Hello, good afternoon, everyone. My name is Minjian. I'm from the University of Illinois at Urbana-Champaign. Just talk. Can everybody hear me? Okay, so this is a joint work with my dear collaborators Daniel Lim and Umang Mathur from the National University of Singapore and Mosaad and Mahesh from UAUC. The talk will be about some algorithmic improvement on dynamic risk detection under a specific context called sampling. Okay, so let's start with data race. A data race is a pair of concurrent accesses to shared memory without proper synchronization. It is a crucial concept in concurrency testing, given that many modern compiler optimizations and memory models assumes or requires data race freedom for its correctness. For instance, data race is an undefined behavior in C11, which means that the compiler can make whatever assumption it wants to make to the instruction that causes a race, including that instruction does not even exist. And another example will be Java, which usually requires data race freedom for the program to behave in a sequential consistent manner. So one way to test data race is dynamic analysis, which in some sense focus on the monitoring problem that for a given concrete execution, it detects whether this given execution has a data race. Dynamic analysis is typically sound, and by sound in testing, we mean that whenever the approach says the execution is buggy, it must be buggy, okay? But it can still miss bugs because it only checks for one execution. It does not explore the full interleavings. Dynamic analysis typically is completely automated, and therefore it is widely adopted. So there have been several widely adopted tools that does dynamic analysis on races, with thread sanitizer being one of the most prominent. But the base logic behind these tools is a classic algorithm called the vector clock algorithm, which detects races by sort of capturing the causality between events via vector timestamps. This algorithm runs in time theta n times t, where n is the number of events and t is the number of threads. Monitoring a program with this vector clock algorithm can result in a very huge overhead. And I'm pasting the disclaimer from T-Sign's official website, which is basically saying that running your code with T-Sign can make it very slow. Okay? So one of the popular ways to mitigate this overhead is sampling. And the rough idea of sampling is that you only do risk detection on a small set of events. And the high-level intuition is that meaningful behavior information of the program can often be extracted without analyzing every event into full detail. So sampling-based risk detection, again, they are still typically sound, namely we do not tolerate any false alarms. And they have much lower overhead comparing to the other case. And they detect the races with some probabilistic guarantee, depending on how the events are getting sampled. So given these advantages, it's not surprising there has been an extensive research on this topic. And sampling-based risk detection centered around two key questions. The first one asks, how do I pick the samples? Or specifically, which memory access events should we sample in order to increase the likelihood of detecting races? And the second question asks, like, once this set is determined, how do we check for races? And the majority of the period research has primarily focused on the first question. They proposed many efficient strategies, including random sampling or combined with static analysis to identify the instructions and memory locations that are more likely to be buggy, or even rely on user-guided information. However, the second question, namely how do we check for races once this set is determined, received far less attention. Although many of the prior research had attempted to address the second question with some heuristics and optimizations, they lack an algorithmic foundation, and the common fallback remains to be running the vector clock algorithm, but ignore all the events that were not sampled. And in the worst case, this naive approach have the same running time complexity as the case without sampling. So this leaves a very interesting open problem that if we can design an algorithm that symptomatically beat this naive approach. Okay, so in our so this is a major focus of our paper, and in our paper we formulate this problem, namely the second question, as a marked analysis problem, which basically asks that for a given execution with S marked event, and determine if any of the two marked events are in race. And here I'm providing a summary of our result compared to this naive algorithm I just mentioned. So both of our algorithm and this naive algorithm runs in a one-pass streaming manner, and they are both sound. Again, by sound we mean that we do not report any false alarms. And for the running time, the naive algorithm is the same as running the vector clock algorithm without sampling. It runs in time theta n times t. And our algorithm runs in time of OST squared, where S is the number of marked events. Okay? And both of the algorithms can be efficiently parallelizable. At the end, it's sort of worth mentioning that the algorithm we proposed will output exactly the same as races as this naive approach. Here we also show some highlights of the evaluation. And we show that when the set S is relatively small, like 0.3% comparing to the size of the execution, our algorithm can reduce around 37% of the overhead introduced by the naive approach, and up to 70% on some benchmarks. And it's sort of important to notice that the naive algorithm also benefits from sampling because it also ignores the 99.7% of events that are not sampled. And with a relatively larger sampling rate, like 3%, our algorithm still reduces around 20% of the overhead and up to 37% on some benchmarks. Okay, so let's now get into some technical thing. Let's firstly give a definition on data arrays. So for a given concurrent execution, we firstly consider two partial orders. The first one is intra-thread ordering, which is just a total order on the events of the same thread. And the second order is a total order on the accesses on the same lock, which means we assume sequential consistent behaviors on lock accesses. And the happens before relation is the smallest transitive closure of these two partial orders. And we see that two accesses form a race if they are not ordered by happens before and they access the same memory location and at least one of them is a write. Okay, so the vector clock algorithm works in the way by assigning every event a timestamp. The timestamp stores the knowledge of the event about how many events happens before this particular event E from each thread. In some sense, it's like the number of events E knows. And it's kind of intuitive that this timestamp can be used to capture the happens before relation between two events, because let's say E1 happens before E2 if and only if every event E1 knows is also known to E2. Okay, and the vector clock algorithm operates in a very classic way like a message passing algorithm, in the sense that each thread is maintaining its own local information, and they communicate this information via lock accesses, namely like release and acquires. More specifically, what we can think the release is the sender of the message, and the acquire is the receiver of the message. But this communication is not free. It is achieved by vector clock operations. Intuitively, when I receive an information, I would like to learn from the information I received. So the vector clock data structure supports this operation called the join, which takes two vector clocks and returns the pointwise maximum. And when I send the information, I would like the lock to carry my knowledge. So I just wanted to copy whatever I have. So the vector clock also supports this copy operation. And both of these operations runs in time all of t. So that is why the total overhead of the vector clock algorithm remains to be theta n times t. And this is also why the naive approach, even when we are ignoring a lot of memory accessing event, still remains to be n times t. That is, we cannot omit these communications in order to be sound. So our algorithm is built upon this vector clock algorithm, but we have three observations that allows us to achieve this better running time complexity. So the first observation is that we can simplify the local timestamp so that there is a bound on the number of updates each thread needs to update its local information. And when the number of communication is far more than the number of local updates, many of them just become redundant. So our second observation says that if we can avoid these redundant communications via something called the freshness timestamp. And finally, we also notice that even when a communication cannot be fully avoided, we can avoid it partially if we enhance the vector clock data structure with some ordering information. And the major contribution of our paper is a formal analysis on how to combine and apply these optimizations so that we can achieve a better running time complexity. Okay. So the sampling timestamp basically says that we can simplify the original timestamp by only remembering the number of marked events that event E knows. And this basically naturally bound the local information a thread kept can be updated. It is bound by S. And it's sort of very intuitive that this timestamp is sufficient to capture the HB relation between two marked events. And the second observation we made is that there is this freshness timestamp, which is like the knowledge of knowledge. What I mean by that is it stores like how many times the knowledge of another thread has been updated that is known to me. This in some sense tells us the freshness of the information. And the high-level intuition is that if I receive an information that in some sense is not fresh to me, I know everything, then I know everything this information is trying to deliver. I can safely ignore it. So a coarse example will be, you see for the execution on the left, if thread T2 receives the information from T1 that has been updated for 10 times in the first communication, then it can ignore the second communication because it delivers the same message. However, on the execution on the right, if the second communication delivers a message that has been updated 11 times, then I cannot skip it. But it's sort of important to notice that I already know most of the information that is being passed in the second communication. And more specifically, there is only one update that I'm not aware of. So if I can somehow identify which entry it is, I can just look into that entry without looking into the rest of the entries. So the way we achieve this is by enhancing the vector clock algorithm with the ordering information. In some sense, now the vector clock, we associate the vector clock with two arrays that stores the information of how the order of the entries that gets updated. And now this special data structure supports a different kinds of join that takes in two parameters. Namely, one is another ordered vector clock, and the second one is an integer k, which basically says I just want to read the last k entries that this vector clock got updated. So in this previous case, all I need to do is just to run this join operator with k equals to 1, because I just want to know the last entry that got updated. And I'm aware of all other things, all other updates already. Okay, and finally, the last piece of this running time of the improvement in the running time is to apply this shallow copy idea, which is sort of quite common in the context of sampling. And the rough idea is that because we can shift the cost of delivering the message into the case when you have to update your local information. Because when you have to update your local information and the information is shared among different delivers, you have to create a new deep copy. But because we showed that this update it can only happen for S times, it also naturally bound the number of deep copies we have to create because we're using this shallow copy idea. And for the experiment, we implement our tool upon thread sanitizer, and we run the algorithm on a system with 64 threads. We tested against the bench-based benchmark framework with random sampling. Namely, we randomly decide the side S in our formulation. And this is, we achieved some sort of, a visible reduction in the overhead, as I have already mentioned, but we believe this overhead can be reduced much more if we are able to optimize the implementation. And we also did some profiling during the experiment. We show that with the second observation, namely this freshness timestamp, we can effectively skip 50% to 70% of the communications. And now equipped with the last observation, this ordered vector clock data structure, in average, we traverse 3 to 6 entries per communication, while the number of threads remains to be 64. Okay, and for future work, I believe there is a need to improve our implementation for better evaluation of the algorithmic improvement. And it's also very interesting to see how this algorithm works with other sampling strategies, like the ones being guided by user information or static analysis. And it's also interesting to see if we can extend the ideas into other settings where communications happen to be dominating. And finally, we would like to know if we can further improve the running time complexity from S times t squared to S times t. Okay, thank you.